So, brief review of the states of matter, solid, liquid, and gas. We're familiar with water in all three states, steam, the liquid water, and solid ice. And here we have illustrations of what the particles look like in those different states. In a gas, there's a large amount of separation between the particles, and so they're really not interacting with each other at all. The particles are moving freely and independently. In a liquid, the molecules are what we call touchingly close. So they're very close together. That's going to leave a mark. But they're moving around relative to each other. They're not stuck in position. So because the particles are so much closer together, a liquid is much more dense than a gas. In a solid, we also have touchingly close particles, and so the densities of liquids and solids tend to be close to each other. Here, the density for water, 0.998 versus 0.917. Oops. What did I do? There we go. Whereas the density of the gas is very, very low in comparison. But now the particles, although they're moving, they're vibrating in space, and they're not moving relative to each other. So when we first talked about the states of matter at the beginning of the semester, I talked about the three states of students, right? So right now, you guys are in the gas state, right? Super separated, moving independently from each other. When we used to get together for lecture and everybody sat in a chair and just wiggled around a little bit, you were in the solid state. We were relatively organized because there were rows along the benches, and people stayed where they were until the lecture was over for the most part. Liquid state was like lab, where we're all together in the same room, very close together again, and yet we're moving around, but still you could literally reach out and touch someone. So these slides are now going to be a little bit repetitive because I basically always talk about them before I get to them. So freedom of movement is a big difference between solids and liquids. And here we have a summary of the different states of matter, differences in density, shape, volume, and relative strength of intermolecular forces. Ouch! Yeah, those kitten claws, very sharp. Dog? It's a circus. So, because the particles in a liquid are free to move about relative to each other, they will take on the shape of their container. But liquids cannot be compressed. So that's good news because otherwise hydraulic brakes would not work at all. So in a liquid, if you put it into a container and like a syringe and you try to compress it, it's not going to compress. Maybe a teeny tiny bit, but nothing significant. Whereas if you put gas in a container, like a syringe, if you put enough pressure on it, you can condense the gas into a liquid. And so the volume of the gas is variable. If you guys have any questions at any time, please just let out a yell or type something in the comments. We can classify solids by how their particles are arranged. In a crystalline solid, like the picture here, there's order to the particles. There are lots of different ways that the particles can arrange themselves, and we'll look at that more in chapter 13. But a crystalline solid is going to have a regular repeating pattern in 3 dimensions. The other possibility is called amorphous. Prefix a means without, and morphous refers to shape, so without shape. And so, if you talk about characters in science fiction or whatever that can morph, they can change their shape, right? So this would be something like glass or rubber, where the particles are randomly arranged. In a solid, they're not going to move relative to each other, but there's no pattern to how they are arranged. So here's a quick question. Which state of matter is compressible? Solid, liquid, or gas?
of the above, technically, in theory?
Technically, yes, all states of matter can be compressed. Which one can be compressed significantly?
A gas.
A gas, yeah. And sometimes students say, well, what about something like a sponge? You can compress that. Well, the reason you can compress that is because it has big empty spaces in it, and so the molecules there are just being pressed closer together, and so that's not really a compressible solid. But solids and liquids are not significantly compressible. So we are familiar with state changes, especially with water. We understand that if you have solid water, which we call ice, and you heat it up, it will melt and become liquid water. And if you heat that up, it will turn into a gas. It'll evaporate or boil. These changes happen due to changes in temperature. You add heat and the states will change. If you want to reverse those changes, you can take a gas and cool it down to become a liquid. You can cool a liquid and freeze it into a solid. We can also induce changes in state using pressure when we're looking at the gas-liquid transition. If we reduce the pressure on a liquid, we can cause it to turn into a gas. We can cause it actually to boil at a much lower temperature than it normally would. If we take a gas and we increase the pressure on it, we can increase the pressure to the point where it will actually condense. So that's something that happens in the compressor of your air conditioning, which you may be starting to use, or the in your refrigerator. So they're using the compressing and expansion of gas to cool the inside. So if we look at a liquid propane cylinder, this might be something you have in your backyard to grill hamburgers with. LP stands for liquefied petroleum. It's mostly propane. And inside that cylinder is liquid propane, and then there's a space above it where the gas phase is present. And we have a valve here, and this thing, of course, is under pretty high pressure. When you open the valve, can you take this somewhere else? When you open the valve, the molecules that are in the gas state here can escape, and those will go hopefully through the hose and into your grill where a flame is lit and you're making hamburgers. As these particles leave, the gas state molecules leave, they're going to be replaced by more evaporating from the liquid. No, seriously, dog. Here, you can go play with that outside. Go. She found a bag of corn chips with some crumbs in it. It's like, fine, go eat them, but man, you're making a lot of noise. Not far enough. So let's look at this conceptual question. Here we've got a sample of liquid water. Which of these diagrams, A, B, or C, best depicts the vapor emitted from a pot of boiling water? You can type your answer in the comments, or you can say it.
It's going to be A, right?
Yes, it's going to be A. So what are we looking at here? Well, here we have our little Mickey Mouse water molecules. In panel A, we see we still have those Mickey Mouse water molecules, but now they're separated from each other. In panel B, the white, which is hydrogen, and the red, which is oxygen, are now separated from each other, and they formed hydrogen molecules and oxygen molecules. This is not a process that occurs when water boils, because when water changes state, it remains the same substance. And over here we have individual hydrogen and oxygen atoms also not something that happens when a state change occurs. Anybody have any questions about that?